Thank you very much, Mohammed, for the introduction. I'm Alessandro Fantilli from Polytechnic di Torino, and I'm going to present a joint research with my colleague Daria Jozbek from the Polish Academy of Science in Warsaw. I'm talking about the effect of hydraulic cements on the behavior of bull reinforced mortars. This is the outline of my presentation. I will start with the motivation of this work. Then I will show you the results of some tests on cement-based mortars, and in this case, we are using different type of cements in these specimens. And of course, all of them are wool reinforced. Then I will show you the results, and I will draw some conclusion, and I show future works as well. So, I think that comparing to steel from end-of-life tires, wool is quite similar. We have a huge amount of wool, which is nowadays a special waste because we do not use the wool for our clothes, and we prefer import the wool from other countries, such as Tasmania or similar countries. So the wool is a waste, and in particular, it is a special waste because it needs our sterilization before the disposal. So this is a problem, and it is estimated that there is 150 million of tons per year of unused wool. So the idea is to use this wool for reinforcing cement-based materials. And you can see here the properties of the fiber which can be obtained by a flake of wool. As you can see, there is not only a single diameter, but you have a dispersion of diameter and of length of this fiber. But if you see the diameter, 0.02 millimeter, is more or less similar to the diameter of plastic fibers, and in this case polypropylene fibers, that is generally used in reinforced concrete or in cement-based mortars in general. And also the length is, in this case, the average length is 16 millimeter for wool and 15 for plastic fibers, and the strength 250 for megapascal for wool and 350 for polypropylene fibers. So the red values and the black ones are more serious. The wool filaments are quite similar to the polypropylene fibers. So it can be used to reinforce concrete or cement-based mortars. However, we have a problem because if we cast fiber reinforced mortars by using wool, we have the problem that you can see in these two pictures. Wool within an alkaline environment is corroded, and you can see after storing the specimen, the mortar specimen, for 27 days in water, you observe on the cracked surface these holes, and in these holes, before curing, fibers, wool fibers, were present. And here you can see the empty channel previously occupied by a fiber, a wool fiber. So in other words, there is the so-called hydrolysis of wool in alkaline environment, and so the use of wool in cementitious composite is a problem related to durability. For this reason, we try to obtain good mechanical performances, and in the same way, we have to guarantee the durability of such elements. For this reason, we would like to investigate the cement-based composite made with different cements. Here we have three types of cements, or Portland cements, with high alkali, with normal content of alkali and low alkali content. These three types of cement, labeled with H, N, and L, are classified on the base of the Na2O equivalent content. So we move from 1.1% to 0.04%. So we would like to see if the use of low alkali, in particular cement, and so we would like to see if we can reduce the pH and avoid the hydrolysis of wool, maintaining the fiber reinforcement in time, and of course also the toughness with the time. We cast 12 mortars, and in particular 12 series of specimens. As you can see, the first letter is related to the type of cement, normal content, low content, and high content of alkali. So number one is referred to specimen without any reinforcement, and it was cured by in room conditions. The same is also valid for the 2 and 2 L2 and H2 series. However, in this case, we introduced 10 grams of wool, which is more or less 1% in volume of fibers. The third series, the third 4H series, is related to the same content of wool and cement, but in this case, we stored the specimen after casting 27 days in water. And finally, in the number 4 4H series, we cured the specimens 3 days in water, 1 day after casting. So in total, we have 12 series. For each series, we cast 3 specimens. So in total, we tested 36 specimens in 3-point bending. These are the pictures related to the test. It was a very well-known test performed on mortars, and it is ruled by European standards. In this 3-point bending test, we obtain the load deflection diagram, and from this load deflection diagram, we can obtain the strength. P is the maximum load applied to the specimens, and of course also the deflection at peak of load. With these two values, and of course with the Boole curve P delta, we can define the post-peak behavior. We normalize the load with respect to the maximum load, and of course we consider only the relative displacement or the relative deflection after the peak, delta minus delta at peak, up to 202 millimeter. In this way, we have the area defined by this diagram, which is such a kind of fracture toughness of the material we are going to use. If you want, this post-peak behavior can be simplified by a bilinear relationship like this one. And from this bilinear relationship, we can compute not only the AF, the fracture toughness, but also Y1, which is the post-peak residual strength after the growth of the crack. So, which is an important parameter for evaluating the capability of the fiber to bridge the crack after the growth of the crack. So these are the results in terms of maximum load, deflection peak, and in particular Y1 and AF, which is the area under the post-peak diagram. And we also observed the microstructures of the mortars after testing them in 3-point bending, and these are the picture taken on the fracture surfaces. So let's see and investigate now the results. As you can see here, I have reported the maximum load as a function of the alkalinity of the cement we are going to use. As you can see in this picture, as the content of alkali increases, also the strength of the material is increasing. This dashed line is the situation in which you don't have any reinforcement, so plain mortars made with the 3 different cements, and of course L, N, and H2 are the mortars reinforced with 1% in volume of wool. In this case, you have the specimen cured in at 20 Celsius degree with a relative humidity of about 50%. If you introduce these specimens in water, you can see you have a more or less a reduction of the strength, and you cannot see a great difference between the different types of cement with respect to the maximum load, as you can see in the previous one. This is the case in which the cement were stored 27 days in water. If only 3 days in water, if we left the specimen 3 days in water, of course you have more or less the same behavior, but anyway the strength is lower because we have such a kind of early stage strength of concrete. But this is only the effect on the strength. In our case, we would like to see the capability of fibers, so we have to observe what happened after the cracking, so in the post-peak diagram. and in particular on Y1. Y1 is more or less the percentage of residual stress with respect to the strength of material. As you can see,
2 minutes left.
Okay, as you can see, as the content of alkali is increasing, you have a reduction of the residual stress in all the specimens, and from 30% of L2 we move to 0.05 related to the maximum content of alkali. Of course, in water, you cannot see any difference among the among the different cements, because the hydrolysis is accelerated by the presence of water. So, and the same results are similar for AF. So what happens to the hydrolysis? If you see here, after 3 days, only part of the boule is degraded, not all the boule. So for the maximum alkali, you have such a kind of residual stress. But if you left 27 days, you can see the boule is completely degraded. So only the whole remains, not this one. And as a consequence, you have a reduction of the strength. Conversely, the better performances of L2 is related to the fact that if you use a low alkali cement, after 27 days outside water, you can also observe the presence of boule. So the boule resists to this type of alkali and of environment. So these are the conclusion. The strength increases with the alkalinity of cement, and the capability of the fiber to bridge the crack surface can be only guaranteed by the presence of low alkali cement and without water. I just want to show you that this final slide, in which we observed, we compared the plain concrete, the wool reinforced concrete, the red one, and these are the polypropylene fiber reinforced concrete. So as you can see, in low alkali cement, the performances of the wool and propylene are the same. If we increase the content of alkali, you have a decrement of the performances of wool, but pay attention, also the polypropylene fibers degrade in alkali environment. So thank you very much for your attention.